Great, thank you, Linda. So our first speaker tonight is Bob Napier, and he's going to talk to us about an internet-based observatory operation. So welcome, Bob.
Thank you, Mike. I'm Bob Napier, and I've been a member of Skyscrapers for a little over half a century now. My first contact with Skyscrapers was in 1957 at a meeting at Ladd Observatory. Professor Smiley was giving a presentation on the Sputnik launch, which was in October of '57. I think it was November, December that he gave that presentation. The Skyscrapers was there, and that was my first contact. I was a freshman in high school at that time, sophomore. So it's been a long time. My first real interest in astronomy, though, started on the plains of Kansas. Back in the mid-50s, I was living in Wichita, Kansas, and it got very hot. It wasn't unusual for several days or weeks to be up to 95, 100, 105. And it was tough sleeping inside. And a bunch of the neighborhood kids would take our blankets and bedrolls outside. And we started noticing these streaks of light in the sky. And we finally figured out they were meteors. And that prompted me to want to look at the moon and Jupiter and Saturn a little more. And my first telescope cost me $1.98 at a toy store in Wichita. One of my friend's mother worked at that store. So I often went in there and I saw this spyglass kind of telescope. I mean, it was really not very well constructed. Probably plastic lenses and a leatherette covering tube. But it did show the craters in the moon and satellites of Jupiter and Van and Saturn. So anyway, that was my first telescope, $1.98. This is my current observatory and telescope. On the left is the garage I had built in the early '80s. And as you can see on top of it, it's a roof structure. I designed it to be on top of that garage, away from the ground air currents. The telescope was supported by a 16-inch diameter concrete pier that went from the ground level of the ground level down here up to the base of the attic. Let's see. Some sort of message. Okay. So originally I had a 16-inch f6 Newtonian, which is a pretty large scope. And I used it for about 20 years. And I currently have there this scope. It's a 14-inch Newtonian that I bought in 2003. It was one of the first models that came out, the GPS series. It has a GPS sensor pod on the left arm there on the scope. And when you start it up, it automatically sort of aligns itself. It gets a time signal from the GPS satellites, and it always keeps a very accurate time base. It also gets the exact latitude and longitude location of the Earth, which is, of course, critical to finding anything in the sky. You need a time base, and you need latitude and longitude location. So I've used that scope now for the last 20 years or so. I haven't actually looked through this scope in probably 10 or 12 years. I no longer have any real eyepieces for it. I gave those away years ago. And it's almost strictly imaging, for digital imaging. And I did quite a bit of digital imaging of all kinds of various things, galaxies, clusters, and fainter deep sky objects. About 6 or 7 years ago, one of the speakers here at Skyscrapers was a fellow by the name of Dennis Conte. And he's a member of the AVSO, and his talk here was about exoplanets, the planets that were orbiting other stars. So that was an interesting talk, I thought. So the AVSO offered a course in exoplanet observations, and he taught that course. I took it, and I started trying to play around with the software and how to do exoplanet imaging. Now, you're not actually imaging a planet. You're imaging a light curve of the eclipse when that planet goes in front of the star. And you generate, through the software analysis, you generate the characteristic light curve of that eclipse. And the reason that you need that is for the Webb Space Telescope. The Webb Space Telescope wants to do detailed analysis of these exoplanets, especially their atmospheres. Well, the Webb Telescope costs about $10 billion to place it in orbit where it is around, it orbits the sun, not the Earth. But it's directly opposite the Earth. So the point is, you don't want to waste $10 billion investment trying to observe something that may not exist. So what amateurs do through organizations like the AVSO and of course NASA is try to observe these exoplanets to verify that they have a periodic transit across the star and the light curve matches what you think an exoplanet should characterize is that the light fading goes through in front of the star. So let me just see if I can. As I say, I haven't looked through this scope in probably 10 or 12 years, but I do a lot of digital imaging through it. And in about 2000, there's a fellow in Arizona, he was a deputy sheriff actually. He wrote a lot of observatory control automation software. And this software sort of forms the heart of digital remote imaging to now it's a server that controls the observatory. You interact with a server with the web browser. Now here's my my web server through this software. It's called ACP, Astronomy Control Program. I actually helped develop and improve it here at Seagrave using the 12-inch. I would look up and do presentations in the meeting hall remotely from there. We didn't have internet at the time here. So for NASA presentations, NASA Solar System Ambassadors Program, I would do these imaging presentations here. So over the past 20 years, it's gradually improved to do an awful lot of good things. And if you want to do just a single image of something, it's got a dialogue there where you just put in the name, and like it has M96 there. And you say to get coordinates, it goes into its catalog, and there are thousands of catalog objects. And it pulls up the coordinates of that object. You fill in the observation time, duration of exposure, the filter, and the binning factor of your CCD or CMOS chip imaging. And then you can just acquire the image. Then it will initiate the observatory operation of the telescope. It will move the telescope to those coordinates. When it gets to the coordinates, it turns over control to your imaging camera. Now, I use Maxim DL. Well, that's actually, I think, the only preferred camera control software. So Maxim DL takes over and starts taking the image. This is for a single image. For a color image, you get more in the dialog there. You fill in the filters that you want for the color separations and the exposure times, etc. Okay. Well, those were the simplest things. Now, the next thing, multiple objects. As I mentioned, the exoplanet is sort of my main focus now. And to do an exoplanet light curve, you need hundreds of images. Now, I'm not, especially cold weather, I can't take the cold weather anymore. To take hundreds of images at a certain pace, certain exposure, well, I don't do that. ACP, the control program, has a scripting language that you can write a basic script and compile it, and it will do the work of taking the hundreds of images every so often to do some exposure. Now, the software used to analyze that, let's see. Software to analyze these hundreds of images is, I use AstroImage-J. AstroImage-J is software that was originally used by the National Institute of Health for MRI imaging, where they took three-dimensional slices of your body and rotate it and see the internal structure of your body. Well, astronomers at the University of Louisville adapted it for exoplanet imaging, and it's really a two-dimensional analysis now, time versus photon flux. Now, the photon flux from the transit of the planet in front of the star is in a few thousandths of a magnitude. So it's not something that the human eye can discern. But your imaging camera, when it's all well calibrated, can detect these very light faint dips. And that's how you construct the light curve. But each dip is only a few thousandths of a magnitude, 10, 12, 15. Now, just to show you, I'll scan through a small sequence of an exoplanet transit star. This is just the raw image. And you can see there's been some clouding or haze going in front. It clears up a little bit. And there goes, you can see it, haziness. Again, these are unprocessed, uncalibrated. Now, if you want to see at the individual frame, each frame has a database associated with it. It's supplied by the software. And there's an incredible amount of detail about the temperature of the sensor, the resolution of the stars, full width, half maximum. Incredible amount of detail that goes with the analysis of the software of the image. Let's see. So there's a tremendous amount of technology involved in this and a tremendous amount of understanding. I certainly don't understand all of the nitty-gritty details of the astro image data analysis software that goes with this. But ACP is the heart of the whole system. It controls the observatory telescope, controls the camera, and the program, the script for each exoplanet transit. You can extract that from a Swarthmore College database, which is financed by NASA, and you can specify when you want to observe a certain exoplanet according to your scope, what magnitude the star is. I usually go up to 14th magnitude, which is about the limit, I think. So that's about it. Yes, sir.
How do you find out, or who do you ask? How do you find out when the likeliest time is that the planet is going to pass in front of its star?
How do I find out when?
When, okay, it takes a planet 20 days to go around a star.
Yeah.
You don't look at that star for its entire period of time. Somebody must tell you when it's likely that it's going to pass in front of the star. How do you get that information?
Okay, initially the exoplanet got kicked off with a Kepler satellite telescope mission back in 2012 or somewhere around there.
All right.
It stared at a very small part of the sky. In 2018, it was called the TESS mission, TESS, Transiting Exoplanet Survey Satellite. And it found thousands of these candidate planet transits in front of the star. You can only see the transit if the orbits are aligned to our line of sight. So the job of the amateur citizen scientist is to keep observing these candidates and see if it repeats like a few days. These planets orbit very, very fast in a matter of a few days. So it's a calculated transit time and then this observed transit time. What we go by that Swarthmore College database is we look up what planet transits will be observable from your area when, and that's what you go.
Okay, so it's the Swarthmore database from TESS and from Kepler that causes you to go look at that particular star on that particular night.
Right.
Okay.
And that's why that little script program that I write, I load it up into my server, and when the time approaches, it starts up and it moves the telescope to that target star, and it starts imaging for however many hours. Usually I don't go more than 2 to 3 hours. But it's hundreds of images.
Oh, yeah.
But that's from the test satellite. It's basically what you look at. And again, that's make sure you don't waste time on the Webb Space Telescope observing something that there are other things that can mimic planet transit. Other things. Could be an eclipsing binary star. It could be a dust cloud that's orbiting the star in its formation. It could be dark spots on the star. There are other things that the characteristic light for a planet is kind of helps determine that it's true.
Sure.
Any other questions for Bob?
What about the roof? Are you climbing up to push the roof or do you have it on a motor?
Unfortunately, I have to climb up. There's an internal stairway, not external. There's an internal stairway in the garage that I climb up into the attic area, so to speak, and I just push the roof back. That's that's the only thing I really have to do. Once I power up the scope and hone the position, I go back inside, I connect my web browser up, and I start doing whatever I want to do. And if the scope somehow ever gets lost, like it wasn't honed properly, there is a function in ACP that will take an image of the sky regardless of where it's pointing, as long as it's pointing at the sky. And it'll plate solve that to figure the coordinates of the star, and use the Hubble guide star catalog to resolve where the scope is pointing and synchronize it there. It goes on its way.
All right, thank you, Bob.
My home base is Barrington. And I was interested in having a telescope that I can expand the heavens. But Barrington isn't a very good place to do it. A lot of light. And I had a son that lives up in Pasco. It's a lot darker, a lot nicer than you. I looked in the sky telescope and saw this ad in Canada. Being able to get a outfit that I wanted and made contact with them. And that was back in, I think, around 2019. And made contact with them and purchased the outfit. They said that it would be within the next 6 months that we get this thing. I got it in October of 2019. And started building this observatory. My three sons were the builders that helped me out with it. I didn't do much myself, but they did the work. And that's what you'll see is the construction process that we went through in getting this all set up. The pictures that you'll see are pretty self-explanatory, and I won't need to talk much of anything about it. Maybe my boys can pitch in on various kinds of things and tell you a little bit about it.
It's coming along. It's almost there.
Oh, by the way, the process I sent away to the south that I got T-shirts for you. Hats that have the same thing on them, and I got a mug for them too. And, so every once in a while, they use the mug to celebrate.
Wonderful. Thank you.
Can you get rid of that thing?
That was all me, my morning. All right. Okay. Sorry. Nice.
This is the area where we located it. And it's in at Mike's home in Pasco. He has a little 9-acre farm, a lot of animals.
Yes.
These are the buildings. In my right is Mark. In the background is Joel. And then after me is Mike.
Took a lot of concrete.
In fact, originally we didn't have enough.
Yeah, no.
Okay. Joel and Mike
I'm sorry.
to work.
I did that.
And here they're setting the frame for the base.
So we originally had a smaller concrete pad there with a little roll off that looked almost like an outhouse pretty much. That just covered the scope mount. And it didn't work out all that well. And then he found the observatory that we have now. So that's why there was a square and we poured a circle around it. Just give you a little bit of background. The concrete? What do you do? Is that 6 feet? I think it's maybe a little bit more than 6 feet in diameter. Yeah, I believe. Oh, actually, no. Sorry, he asked me what the diameter of the observatory is. I believe it's about 6 feet. Could be.
Well, the next thing here, building protective barrier, and why, you'll see in the next slide.
Part of the construction crew. So.
Package arrival was October 9th, 2019, home from Canada. Piece by piece, we unpacked it.
It's made out of something like like they make kayaks out of. It's like a rotationally blow molded or something like that. It's that type of material though. So you can see around the I don't know. Those are like rollerblade wheels that the whole top section rotates on.
Your idea?
No, it was part of the kit. I don't think this company's in business anymore. But no, it's all part of it. The top just kind of sits on those rollers, and then there are other rollers on the bottom to keep it from, blowing off. So it is held down, but yeah, it just kind of rotates around on those wheels. And then the dome one half, kind of, I don't know, it's clamshells inside the other one. You just kind of push it open when you're ready to observe. And you can see the side in the foreground's slightly smaller, so it fits up under the other one. The only unfortunate thing is that the door is rather short. It's kind of tough to get in, especially for my dad. So. And then we just put some wiring in there so we could have some power.
The ultimate objective too is that hopefully we can even be in the house and observe what's up under the telescope. And I have to have that because I'm no longer steady enough to look through the scope and see things.
Does it get hot in there during the day, during the summers?
Yeah, it does. Just got some.
Mike did all the electrical work.
It's just a concrete pier that we put in
That's beautiful.
stand. Thank you. And yes.
My telescope isn't as big as going. Can't see as far either.
Gets the job done.
And here are part of my family, Beth and Mike, and Stella and Lily. And with Mike at their home, sitting in the shell.
Yep.
That's it.
Do you have any trouble observing the zenith with that
Well,
design?
the,
Off center in the.
yeah, when we put that in there, I think we slightly offset the mount, but it wasn't enough, so, I welded up a mount that is even further offset and, it's not as rigid as it should be, so you do get some vibration in there, but it offset the whole thing and maybe another foot, which is really probably what it needed in the first place, but we kind of messed that up. So,
We do have are able to see most of the plants.
yeah,
They're above the trees.
And you could just say, and you just manually move the.
yeah, everything is, yep,
That's nice.
it's done, yep.
Other question? Okay, thank you.
Next up, we have Mark Munkacsy. That's going to tell us about the anticipated nova and T Corona Borealis, right? Something that's supposed to happen somewhere between now and September, they tell us. So we want to get a preview here from Mark.
Hi, I'm Mark Munkacsy. I am a 30-year member of the AAVSO, both member and observer. I've got something above 30,000 observations I've submitted to the AAVSO. And I bring that up not because I'm going to talk about the AAVSO, but because this story of the star T Corona Borealis highlights what the AAVSO does today and what it's been doing for a long, long time now. So T Corona Borealis, as Michael indicated, is expected to go into outburst any day now. It is a recurrent nova, which is a relatively unusual star. When that happens, we can expect T, which is sitting outside, just outside of the crown of Corona Borealis, to become perhaps the brightest star in the constellation, certainly at about the same magnitude level as the brightest stars that are in there. It's expected to be a very short outburst. May only be 24 to 48 hours that it is that bright, and then it's expected to go into its fade beyond that. Astronomers have a whole spectrum that they've defined of cataclysmic star behavior. And it ranges at one end from flickering of a star, flickers that may only last a few seconds, to supernova at the other end, where you've got something dramatic enough that it's completely upsetting the fundamental structure of the star, or the star simply ceases to exist. A classical nova sits kind of in the middle of that spectrum. A recurrent nova is a different kind of an event than a classical nova, but it's in that same part of that overall spread from the really quick to the really dramatic. So let me start off by apologizing for this slide. Normally, somebody's going to stand up here and they're going to tell you about what you're going to see when this star explodes. However, instead of telling you what you're going to see when this recurrent nova explodes, I'm going to tell you more here about how a classical nova happens. The reason for that is because astronomers today really don't understand what's going on in the recurrent nova. And I'll touch on this a little bit more in a few minutes. But in a normal nova, you've got two stars. You've got a big star, physically big, and you've got a white dwarf. And the physically big star, often a red giant, has expanded to the point where its outer boundary goes beyond the point where gravity is balanced between the two stars. And as a result of that, stuff is getting pulled off of the red giant and falls onto the little white dwarf, which is a dead star. It's a star that's completely exhausted its fuel supply. So now you have this stream of good star stuff that's landing on the dead star. And that accumulates there until it reaches the point where it ignites. And it ignites in a fairly spectacular fashion with a shock wave that propagates around the surface of the white dwarf as it goes through this thermonuclear event. We see it as a star that suddenly becomes bright by quite a few magnitudes from what it was like prior to that outburst. However, as I said, T Corona Borealis is not one of those classical nova. It is a recurrent nova because it's done this before. It's also called the blaze star. It has outbursts about every 80 years or so, although there's only a couple that have been positively identified recently. So the most recent one was in 1946. Prior to that, 1866, there are some historical records that may be describing this star. But when you go earlier than 1866, it gets kind of difficult to correlate what's been written down with the behavior of the star. What you see here on the right is the light curve from the 1946 eruption of this thing, where it sat there at magnitude 10, which is where it sits. I have no idea where it sits at this moment, but as of last night, that's where it sits today. Back in 1946, it peaked at just over magnitude 3. And as you can see here from the graph, that was a very short peak before it dropped down. For that eruption, there was a secondary peak that occurred several weeks later. Astronomers are not certain what causes that second peak, but I'll come back and talk about some of the ideas that may explain that in a minute. As you look at that historical record leading up to the 1946 eruption, there was a dip about a year earlier, and also shortly before the eruption, there was an increase in the brightness of the star. That behavior has repeated in recent months and years. The top left here is a graph that goes back 65 years, so it doesn't go quite all the way back to that prior eruption. What's cool about this is there are 131 points on that graph, and I mention that because downloading that thing took forever as each one of those points was individually loaded. But you can see as you look at that, that in the past year or two, the star's behavior has changed from what it was previously. Down here, you can see the last 2 years expanded from that one up there. A couple things are evident. Number one, the brightness is not overall constant over this time. It is getting fainter, which is a new trend for that star compared with its older behavior. And number two, you can see that there's a periodic fluctuation in the brightness. So it turns out that periodic fluctuation in brightness is coming not from the white dwarf, it's coming from the red giant. And what astronomers understand is that the tidal forces, the tides on the red giant caused by the white dwarf, have stretched the red giant, so it's no longer spherical. It's now egg-shaped. And it's turning so that the pointy part of the egg is always pointed at the white dwarf as the red giant goes around the white dwarf, or as they orbit each other. When we see the pointy end of the red dwarf, we see the star system being fainter than when we see the broadside aspect of the red dwarf. There's more of the star to see, and we see it get brighter. When you go in and look in detail at the light coming from the star, one of the things that becomes evident is that there is no light that's reaching us from the white dwarf. All the light is coming from a combination of the red giant plus a disk, an accretion disk of material that has formed around the white dwarf and is so thick that it completely obscures our ability to directly get light from the white dwarf. What we understand about what's going on in that system right now is that as that material that comes from the red giant swirls around and eventually lands on the white dwarf, that heat, the temperature of the material as it hits the white dwarf is extremely high. And as a result, the energy that's coming out of that is not in the visual spectrum at all. It's all up at the gamma ray level. All of that energy is being trapped in the accretion disk, which eventually re-radiates it as ultraviolet light, a lot of blue, there's a little bit of green and red so we can see it when we look at it. And that is currently one of the dominant sources of light from this system. When that historical data record is compared to recent behavior, you get this prediction, which was published last year, about when the eruption, the next eruption of T Corona Borealis is likely to occur. Their prediction was 2024.4, so 0.4 of 12 months puts us around the 5-month point, which is roughly the end of May. So here we are in the beginning of July, we are in the plus or minus 0.3 window. And that's the basis of this expectation that we will see this star erupt any day now. There's no evidence from the 1946 eruption that gives you any hint that the eruption was going to occur any more than that roughly 6-month period prior to the eruption. So we don't expect any other flags that we can use to judge how close we are to the eruption. Now, what's curious about these recurrent nova, number one, they are extremely rare. So whatever's going on in them is not typical of what happens in these systems. Number two, the distance between the red giant and the white dwarf is much, much bigger than what astronomers are used to seeing in these tightly bound star systems where there's a lot of interaction between the two stars. The red dwarf is roughly in a Venus kind of an orbit around, the red giant is in a Venus kind of an orbit around the white dwarf. The white dwarf is heavier, by the way, than the red giant. The orbital period of 228 days is double the period of that fluctuation in the light curve that we saw on the previous slide. Nobody knows yet what is causing that pre-outburst dip that was seen. Further, the ingredients seem to be there for this to be a precursor to a type 1a supernova. The white dwarf is near the upper mass limit for how big a white dwarf can be before it will collapse. So it doesn't take a huge amount of material coming from the red giant in order to tip the white dwarf over that limit, which is what triggers a type 1a supernova. Finally, and this to me is kind of the most amazing of these mysteries, astronomers don't know whether this outburst or any of the outbursts associated with the recurrent nova are actually an outburst from the white dwarf or whether it's activity in the accretion disk itself. This may simply be a bunch of gas that gets disturbed and behaves in a really dramatic fashion as a result of that. There's some indication from the 1946 eruption that there was a large pickup coming from the red dwarf that was somehow involved in triggering that outburst. Some astronomers have asked the question, could magnetics play a role in this? Is it possible that the red dwarf has things like a magnetic flip that occurs that becomes part of the timing of this 80-some year cycle, and that influences the way material gets collected as it gets pulled off the red dwarf and goes on to as it gets pulled off the red giant and falls into the white dwarf. Nobody's quite sure yet. And so this outburst is being studied to a degree that's really quite exceptional compared with other events that occur up in the sky, because astronomers are hoping to get answers to some of these questions. So finally, I'll finish with a plug for the AAVSO. It's really an outstanding organization if you have any interest at all in citizen science, in contributing to the science of astronomy. There's lots of things you can do. I've listed up here some of the stuff that's unique to T Corona Borealis. One of the things that's nice about AAVSO is it caters to every level of expertise, from the amateur that has never looked at a variable star before, that's where I started, all the way up through professional observers at professional observatories and every level in between. If you are at all interested, you can explore this on your own at aavso.org, or just reach out to me or any of the other AAVSO members that we've got within Skyscrapers. Any questions? Yes.
The outburst that occurs.
Speak loud.
The outburst that occurs, is it a fusion event? Because it doesn't seem to have the pressure and temperature required for there to be a fusion reaction.
So if the outburst is coming from the accretion disk, then it is probably not a fusion kind of event. If it's coming from the surface of the white dwarf, then it almost certainly is. One of the problems we have is the disk is thick enough that we can't see that inner edge of the disk, which is most likely the origin point of this, and we can't see the white dwarf directly. So what we're getting is secondhand radiation that's coming from the system. So at least with the recurrent nova, it's not clear.
Okay.
With the classical nova, it's clear. It is a fusion event, but with this one, uncertain. Yes.
I have a question online.
Go ahead, online.
Can you hear me? Okay. It's more of a comment. To find T Corona Borealis, set your go-to telescope to IC 4587. Index catalog 4587. It's an elliptical galaxy, 15.5 magnitude. I have a C star, and you can't enter RA and deck coordinates yet, but if you enter IC 4587, centers it, and T Corona Borealis is just right above it, the star. So it's very easy to find that way.
That's good to know. I've been encouraging anybody that can image this area to put together or to gather enough images that after the event, you can stitch them together into a time lapse to show what has happened. Because that would probably make for a cool video.
Okay, thank you.
You're welcome. Yeah.
I know there wouldn't be like hard numbers or data, but is there any observational evidence of whenever the outburst was prior to 1946? Do we know if it has any recorded observations of it having these events prior?
So yes, there was a well-documented outburst in whatever it was, 1866 or so. And I have not looked to see what was going on there. That predates the existence of the AAVSO. So all the data that's convenient to me is from the 1946 event onward. But I know it is recorded. Yeah. Steve?
So our core bore is of course the first variable discovered in Corona Borealis.
Yes.
So when was T discovered relative to the 1866 event? Could that tie it to its being labeled as what it is?
I don't know. It's an interesting question.
T was the French. Yeah,
Yeah.
it was the French startup before.
Francine?
Yeah, this is listed as an 80-year progression, for 2 years early. What,
Yeah, that 46 to 24 is what's happening.
yeah, what, is there a reason for this?
Nobody knows the answer, whether there's a reason for this. As I mentioned, there's that whole spectrum of cataclysmic behavior with several different kinds of stars that exhibit outbursts on sort of periodic cycles. However, in many of those cases, the periodicities are only approximate, and the star does its own thing to its own schedule on each of those cycles. And you get these things so astronomers try and pretend they understand it with labels. So they have super outbursts and mini outbursts and standstills and things like that to try and explain how this behavior that would be so nice if it was strictly periodic, it isn't. Yes.
James Webb be able to penetrate the accretion disk?
So the way they're penetrating it is by going to the shorter frequencies. So go to ultraviolet, go to gamma ray collectors, and that's giving them data from the white dwarf and from the inner edge of the accretion disk. So it's kind of the opposite end of the spectrum where they're going to try and get that additional data. Yes.
Are you able to get any alerts or notifications if there's any change in brightness, like if there's a slight brightness of the like
So
energy level?
The AAVSO runs a alert service that you can sign up for that will give you alert notices. I don't know that you can do it specific to this star. But yeah, you can get those kind of alerts.
Yes. So through the AAVSO.
Yes. Yes.
Any other questions for Mark?
Okay.
All right, great. So next up, we have John Kocur, who is going to talk to us about the most recent Aurora that we've had, and I think he's also going to sneak in a couple of eclipse photos from
It kind of ties in with it, you know? Yeah, you'll see why.
My name's John Kocur. Thank you, everybody, for being here tonight. I'm an amateur astronomer, astrophotographer, been member of Skyscrapers for 20 years. And I just love astronomy ever since I was a little kid. And I've seen 4 auroras here in this area, 2 in Douglas, where I used to live, Massachusetts. 1 at Connecticut Star Party, and that was like in the late 90s. And then this was in Connecticut. I live in Killingly, which is where this was taken, right out my front yard. So my friend Barry, who's big into astronomy, lives out in Western Mass, and he gave me a text. Oh, hold on, how do I get that off of there? Exit.
Just click on it.
I don't hit exit, just click
Just
it.
click
Click it. Yep, just click the file. All right, so my friend Barry texted me On the 11th, and I knew that there was gonna be an aurora happening, but I was completely clouded out. And this was about midnight, he said, John, we've got aurora activity out here in Western Mass, he lives in Beckett. And, I said, okay, so I looked out my front yard, nothing, because my front yard faces to the north, completely clouded out. I said, I looked at the weather map and it was starting to move, the clouds were starting to move to the east. And I said, okay, I'm gonna come back out maybe in about 2 hours. And sure enough, it started clearing up, so this was the first shot I took. And, hold on 1 second, I've got settings that I have here, just want to write them down so that I remember them all, just in case you like to know how these were taken. So I live on a reservoir, Alvia Chase, ALVIA Chase Reservoir, and that's on Hartford Pike in Killingly, East Killingly. And this was taken around 2 o'clock, okay? So I live in this area, it's about a 365 acre preserve, so the skies are pretty dark in my area. I was gonna hopefully get some good results, but I still had a layer of thin clouds that were kind of obscuring my view. So this was my first attempt. And then that's the next one. And as you can see, it's not very brilliant, you know, the colors are not very vibrant, but you can see the Big Dipper very clearly there. You know, super, you can even see Mizar and Alcor. And this was taken with a Samsung S20 on a tripod. So it's a 12 megapixel camera that's built into the phone. Right. And this one here was, it's still kind of hazy, not the greatest. You can see the clouds, they're starting to move out. And this, I tried to bump up and pull out some color, so I changed some of my settings. And so this is like a 4-second exposure, and the ISO is around 400. And I didn't want to, and it's a 4-second exposure. I didn't want to go too much more than that, so that I seem to be getting good results with that, but I said to myself, I gotta get to a better location. And around about a block away from here, my reservoir is connected to 3 other reservoirs, and so I decided to go to one that's more wide open. And so that was the last picture I took out on my house. And it's starting to get better, it's getting brighter. And so there's the Alvia Chase, that's like a tertiary reservoir, it spills over into smaller reservoirs. And as you can see, I've got a big, nice panoramic, view here. All right. And by changing the settings, I was able to get a little more color out of it. It seemed to be quite muted, again, because I don't have the perfect conditions because of the clouds are still up there. There are a lot of thin clouds. Over here, there's right there, that's a campsite. It's called Hideaway Campsite, and then there's a couple of cell towers over there. So it's starting to move around and I'm getting more color. There's purples in there now. And you can see that curtain effect. There's more. This looks like the coat hanger, but I know it's not because the Big Dipper is just right there and that's nowhere where the coat hanger is. But it looks, I might have to figure out what that is on star chart. So there it is moving again. You got like a nice purple spike there too. It's easy to see on here. I don't know how can you see it? There's like a purple spike there.
Were you able to see the motion in real time?
Yeah, yes, yeah, I could see it. But it was diffuse. It wasn't super defined like you see like up in Norway or way up in Canada. It doesn't have that really intense shimmering color. It was just the conditions I had to work with. At least I got something. better than a completely clouded out sky. All right, so. And again, you can see it's really got the curtain effect there, you know? It's not super defined, but it's improving over time. Again, you can see that curtain effect there. That one shows up pretty good. They have 100 trees. Now, this picture was taken out in Western Mass by my friend Barry, so you can see the difference. He had better conditions than I had. Right? I'm shooting in a panoramic shot. He's going vertical, so I got a 16:9 aspect ratio. That it's wide field, but it's not ultra wide. So the next one is, that's another one from Barry, that's Western Mass, that's in Beckett. And look at that. Wow. When I was in Douglas, I had one very similar to this in my backyard. It was just magnificent. It was so brilliant. The colors, these auroras are different here than like again in Norway. I guess when you're further up, closer to the pole, there's a lot more, many more lines of magnetic force, but we seem to get these curtain effects, big, huge, wide curtains. There's another one from Barry. Another one there. Yeah, nice one. Look at that one. The tree is backlit by it. It almost has a glow around it, huh? I'll go back to the other one. I went by it too fast. Gotta take in those colors. Again, Western Mass, Berkshires.
Now, is he seeing the colors visually?
Pretty much, yeah. He was pretty excited about it. I was excited to see anything. So the camera in my phone is at 26 millimeter focal length. So that gives me about an 82-degree field of view. And the white balance I'm using is anywhere between 36K and 53K Kelvin. Using autofocus, and yeah, the field of view is somewhere between 75 and 80 degrees field of view. This one was taken down by my friend Jay, lifelong friend of mine, well, astronomy friend anyways, since I met him back in early 2000s. He moved down to Anderson, South Carolina, and I went down there to visit him to see the eclipse down there. So that was incredible. We got good pictures of that. And I did a talk on that in the past. So he got some auroral activity down in South Carolina. This is South Carolina. This is South Carolina. So it's all variable, you know. You got the International Space Station going over. That's the ISS right there. This is my eclipse shot from Burlington, Vermont over Lake Champlain. So Mike said he gave me permission to put a couple of them in. He's giving me the yellow flag here, so I'm almost done. I got like 3 more left to go, 3 or 4 more left. So there's my solar eclipse, total eclipse, and you can see it's kind of hazy because I had to deal with clouds. Those lines of magnetic force are not as well defined, but at least I got it. And I got the diamond ring too, but I don't have it on this slide. And this is my hopefully someday prize winning shot. This was right over Lake Champlain, and you can see why I wanted to run to that pond area to take the Aurora, because from my past experience, this is what I came up with. So I knew I was going to get better Aurora shots if I got over a wide open space, a wide open area, and the water always makes it much more dramatic. So that's why I said to myself, I'm not going to settle for my backyard. I am going to move. I just had to move down, a block down the road. So this is right at totality, within 15 seconds of totality. And it looks, that's the Adirondacks. It looks like the sky's on fire because you got the clouds giving that effect. And if we didn't have the clouds, you wouldn't have that dramatic effect. And there's a boatload of people out there. There's about 7 people in a big, I don't know if it's a canoe, tippy canoe. But there's about 5 or 6 people in that boat. And 2 hot air balloons came over during the event. They were right in the middle of Lake Champlain. They timed it just right, not in the lake, but over the lake. And I was looking on the internet to see if I could find shots from their vantage point, but I couldn't find any. I don't know if anybody had a camera or they fell in the water, you know, but I can't imagine the experience that they had in that hot air balloon. There's 2 of them. And they landed right over here where the boats are. They landed on the peninsula sticking out there, just beyond it. And that must have been just absolutely incredible. So it was an incredible experience. I hope to be able to talk about this further down the road, maybe in the near future. You guys are always looking for topics to discuss. And I love doing astrophotography. You don't need the telescope a lot of times. This is an iPhone. I mean, not an iPhone, but smartphone. And there's a magazine up there, like an online magazine, and they print it out weekly called 7 Days. It's a Burlington newspaper. And they got pictures from all kinds of, you know, observers that came up to visit and take incredible shots. And I got about 5 of my pictures put into that, and so I was happy that they took my photos, especially that one, the one I just showed you. But I have more of these too, and hopefully, like I said, if I do another talk, I can share a lot more of these images with you. And another one. Looks like a mermaid. It's just unbelievable, unbelievable. And the people come up with these creative, artistic ideas that just makes it even that much more dramatic. And it's a once in a lifetime experience. It's just stunning, absolutely stunning. So like I said, my experience up there tied into with what I was able to accomplish over here on the Aurora in my little neck of the woods. And just, this is the last one. I just wanted to show you where I'm shooting at. My focal length is 26, so 84 is right here. So I'm shooting right around between 84 and 75. That's the field of view. And this camera you can push it right to about 13 over 100 and about 115, 116 degrees field of view. I'll have to experiment that on the next one if I get lucky enough to see another Aurora again. So that's it.
Thank you, John.
You're welcome.
So that concludes our program for the evening.